everybody. Today I am going to tell you about second order reaction kinetics, and in which I will tell you what second order reaction is, and I will tell you about the integrated rate law for a second order reaction in which the concentration of both the reactants is same. So come on, let's take a simple reaction of the type A forming products. And suppose if it's a second order reaction, and if we take the differential rate law equation for this, then we have, let me write it over here, minus of dA upon dt will be equal to the rate. The rate of the reaction will be given by, rate of reaction will be given by this term. Okay, and the rate of reaction is also given by K into A raised to the power. We have taken this 2 because the order of the reaction is 2. We are studying the second order reaction kinetics, so we have taken as 2. So this is the expression for the rate of reaction, and this is also the expression for the rate of the reaction. So both these expressions are for the rate of reaction. So we can equate them, and when we equate them, what we have is minus of dA upon dt is equal to K, then that is K square. Okay. This dA upon dt is equal to A square. That is equation 1. A bit of rearrangement over here, and what we get is minus of dA upon, we bring A from here to here, is equal to K into dt. So this is the most simplest form I am telling you. Now we will integrate it between the limits when time is 0 is initial and the final time, and time is t is equal to time is t. Okay. Suppose we are having this, and so initially when time is 0, then this will be, suppose A naught, and the products are 0, and after time t the concentration will be, suppose it is A and the products formed are X. So at this time, now we will integrate this differential equation, and when we integrate it, what we get is dA upon dt is equal to, this is minus K, sorry, this is A square, yes, A square. A square, if we differentiate it, K is constant, as we all know, so it is out of bracket. Now we put the limits between which it is integrated. We put the lower limit and we put the upper limit. Lower limit being A naught and the upper limit being A. Lower limit the initial concentration and the upper limit will be the final concentration A. And here also the lower limit of T and the upper limit of T. Now we know a very important equation of for calculating the integration, x raised to the power n dx, and suppose we integrate it, what we get is x raised to the power n minus 1, sorry, n plus 1 divided by n plus 1. If we solve this, we get this. We apply this solution to this problem, and what we get over here is, let me solve it here, 1 upon, it is 1 upon A square, and it can be written as A raised to the power minus 2. Now we are integrating this A. So what we will get is, we are integrating this, and what we get is A is equal to n plus 1, and here the n is minus of 2. So minus 2 plus 1 divided by n plus 1. N is how much? Minus 2. Okay. So minus 2 plus 1. So this comes out to be A raised to the power minus 2 plus 1 is minus 1 divided by minus 2 plus 1 is again minus 1. minus 1. So if we solve it, it is a raised to the power minus 1. So it will be, this minus is here, minus a minus 1 is 1 upon a. So what we get is minus 1 upon a. Okay. Okay, this was a 1 upon a square 2. Here we can write it in this form, a raised to the power minus 2. And now this minus 2 is our n. And if we solve it like this, what we get is x raised to the power n plus 1. N is minus 2, so minus 2 plus 1 upon minus 2 plus 1. Minus 2 plus 1, and this comes out to be a raised to the power minus 1 divided by minus 1. And when we solve it, this is a minus 1, we can write it like 1 upon a, and this minus 1 is 1, and this minus sign is over. So now we will place this value of this 1 upon a integration over here, and what we get is minus 1 upon a. And between the limits, the lower limit and the upper limit, we will solve it in our next step. And here we will get a t upper limit t and the lower limit t. So let us assume it to be equation number. Let it be equation number 6. Okay. So this is our equation number 6. Minus and minus will become plus. So what we finally have over here is 1 upon. We will place the upper limit over here. 1 upon upper limit is a minus of, this is we will place the lower limit. 1 upon lower limit is a naught. This is equal to a into t, the upper limit minus lower limit, which is 0. This comes out to be a. So this is our final integrated form of the second law equation. 1 upon a minus 1 upon a naught is equal to a. And the integrated rate law can be given by k is equal to 1 by t. K will be equal to 1 by t, a1 upon a minus 1 upon a naught. Let me write it like this. So this is our integrated rate equation for a second order reaction. This is our integrated rate equation for a second order reaction. Now let me calculate half-life over here only. Let me rub it first. Now I will calculate half-life for this reaction, second order rate reaction. And this expression holds true for that type of reaction in which the concentration of both the reactants is same, means A plus A forming the products. But if the concentration is different, suppose A plus B forming, we are having A plus B forming the products, then this equation will not hold well. There will be a different expression. I will derive that also for you. But now I will tell you about the half-life of a second order reaction. So half-life is when half of the reaction has been completed, means the concentration, the A which we are taking, this A is actually A naught upon 2. So I will calculate that from this equation, that is equation number 7. Okay, this is our very important equation, the integrated rate equation for a second order reaction. So now I will tell you about the half-life of a second order reaction. Half-life. Half-life means when half of the reactant has dissipated, means A is actually equal to A naught upon 2. So we will substitute A as A naught upon 2 in this equation number 7. What we get is that we will keep T half over here, a slight rearrangement, 1 upon A into, we have 1 upon A. A will be how much? A naught upon 2. So it will be A naught and this 2 will go to the numerator, okay, minus 1 upon A. Let's calculate it. Very simple. It will be 1 upon A naught, 2 minus 1 is 1, so it will be 1 upon A naught. Okay. So this is our half-life for a second order reaction. Okay. So we can say that half-life is inversely proportional to the initial concentration in a second order reaction. Okay. We have previously seen that for a zero order reaction, here I would like to tell you one more thing. We have seen that for a zero order reaction, we have seen that half-life was directly proportional to, it was A naught upon 2K. So half-life was directly proportional to the initial concentration. And we have seen that for a first order reaction, we have seen that half-life did not depend on the initial concentration. It was 0.693 divided by K. And so, okay, so it was not depending on the initial concentration. A naught term was not there. And what we find in the second order reaction is, for a second order reaction, we find that T half is inversely proportional to the initial concentration. So we can frame a very important generalization here regarding T half. I want to tell you here only. So T half will be, this means T half is proportional to, in which fashion? A raised to the power. If n is the order of reaction, then T half is proportional to 1. This you can see from here. This relation can be derived, and this relation is very important from your multiple choice question point of view and from the numerical point of view also. You can you will be having several numericals from based on this generalization. Okay, so this is our integrated rate law equation for a second order reaction. Okay. This is our integrated rate form for a second order reaction, and I have written in the most simplest way. This will be easy for you to remember and to recall it also. But I would like to tell you about a way in which it is written in your textbooks. So in your textbooks actually they have written in this way. Suppose A plus A is forming products. Okay. And suppose if A is the initial and A plus A is forming products, since they have taken it to be a second order reaction, and A is suppose initial concentration is A and the final concentration is of initial concentration of the products will be 0 when time is 0. Okay, and in your books they have considered that X amount of the product is formed after time t, so this will be A minus X. Okay, the concentration of this A will be A minus X, and this for another one also it will be A minus X. Okay, and then they have calculated. So I have taken this A naught as A, and A will be A minus X. If we substitute these terms over here in this integrated rate law, what you will get is K is going to 1 upon T. It's very simple. And 1 upon, what is A? A is actually A minus X. So it will be A minus X minus 1 upon A naught. A naught is our initial concentration. So you can calculate it in this fashion also. So this will come out to be, you take the LCM over here, it will be A into A minus X, and this will be A minus over here. And here we will be having A minus X, and if you solve it, you will get A minus A plus X upon A into A minus X. So in your books mostly it is written in this form, but it is the same as this, and this is very easy to understand. So I have made it to like that. So it will be X upon A into AX. A minus X. So in your books it is written like that. A will be equal to 1 upon T, X upon A into A minus X. This is your equation for a second order reaction. I wanted to clarify it for you to remove any confusion, because I have taught you in this manner, and your books will be it is written in this, and these both the expressions are in fact same. Okay. So now let's calculate the units for a second order reaction. Let me rubber it. Here I can explain you the units of a second order reaction. We are having this expression that K is equal to then 1 upon t, k is equal to, let me write it again, 1 upon t, x upon a minus x. So we can see that this is our concentration term. Concentration is how much? Moles per liter, okay, upon time. Let us take it as time, okay, time. It may be in seconds, it can be in minutes, and it can be in hours also. Time multiplied by, again, A is what? Concentration. Concentration means moles per liter. And here we are having A minus X. A minus X is again in moles per liter. So 1 moles per liter term, this term gets cancelled with 1 moles per liter term, and what remains here is time inverse. See, look, time is in the denominator, and when we carry it to the numerator, it will become inverse. So it will be time inverse. Okay. Now come on, let's see this moles per liter. Moles is in the denominator. Moles per liter is in denominator. So we can, when we take this liter to the, we'll go to the numerator, and it will become positive liter, and moles, when we take it to the numerator, it will become moles inverse. So this is our unit for a second order reaction. I have calculated from this formula only, and very easy and very simple. Okay, so it becomes moles inverse, liter, and time inverse. Very simple to comprehend. Okay, so that's all for the second order reaction. What type of graphs can we sketch for a second order reaction? As we have seen, the integrated rate law equation was Kt is equal to 1 upon A minus 1 upon A naught. A naught is our initial concentration, and A is the concentration after time t. K is the rate constant, and T is the time. So if we do a bit rearrangement, we will get it in the form of y is equal to mx plus c, which is the equation for a straight line. So if we plot y against x, which is time, then we should get a straight line, the slope of which will be positive, given by the k, and the intercept on the y-axis will be given by 1 upon a. So if we plot a graph between 1 by a and the time on the x-axis, then we should get a graph like this with a positive slope and the intercept on the y-axis given by 1 upon a. Some more graphs can be also be sketched, like the graph between the concentration and the time. It will be somewhat like this, with a high rate on the y-axis over here. One more graph can be sketched like this, between the rate and the concentration. Here I have taken rate and the concentration, and the graph goes exponentially in this form. And one more thing I would like to tell you here now, since I have completed the zero order, the first order and the second order reaction. Let me, if you want to do the graphs of, compare the graphs of the three regarding the concentration and the time, then the graph for a zero order is like this, a straight line, negative slope. And the graph of a first order is this one, yellow one. This is our graph for a first order reaction being parallel to the time axis, since a first order reaction never gets 100% completed. And this is our this graph is our for the this pink one. This is for our second order reaction. If we plot for the concentration and the time, then the graphs are like this. The second order graph is much more steeper than the first order graph, and the zero order graph is just a straight line with a negative slope. So this was all about the second order reaction I wanted to tell you. Thank you so much.